Hello, I am Jean-François from the Centre de Recherche Astrophysique de Lyon, and I will talk to you about spirals, shadows, and precession in HD100453. This is a two-part study about this system, and I will present today the first part on behalf of my collaborators, who you see listed here, about the orbit of the binary. We will start with a description of the system. So HD100453 is a binary star system, and the primary star A is surrounded by a circumprimary disk, which you can see imaged here in scattered light with the sphere. This disk displays an inner gap, as well as two spiral arms here. We can also see two faint shadows in the disk. Those shadows are more clearly seen in a longer wavelength observation, also by sphere here. And these shadows are thought to be cast by an unseen inner disk. Well, this inner disk has since been detected by the VLTI instrument Pioneer, and its relative inclination to the outer disk has been measured to be about 70 degrees. In addition, ALMA also revealed a dust ring composed of larger dust grains, and we can trace faint spirals in the dust ring as well, in this case. And finally, the emission from the CO gas in this moment zero map reveals two large-scale spiral arms, and the overall emission of the CO gas extends all the way to the secondary star. This casts doubts about the previously accepted hypothesis that the orbit of the secondary star was close to coplanar and circular. To summarize the system, this sketch shows from the outside in the outer companion on its dashed blue line orbit, then the outer disk, then an inner companion on its dashed green orbit. This inner companion is not detected, but is assumed to be here and to carve the gap inside the outer disk. And finally, there is the inner disk in green. And you can see that all components appear misaligned or inclined relative to one another in this sketch. The unseen inner companion is the topic of the second part of this study, and I will spend the rest of this talk talking about the outer system, so the outer companion and the outer disk. The outer companion has been observed on the very small arc of its orbit only, and we must do some orbital fitting to recover what is thought to be the orbit of the companion. So in this work here, we took a selection of 7 orbits from the fitting done by Van der Plas et al. 2019. As you can see on the images of the plane of the sky on top and the perpendicular plane at the bottom, many different orbits can be very good fit to the data. And in our selection of 7 orbits, we start from orbit 0, which has a very high relative inclination of 61 degrees, to the purple orbit 6, which is almost coplanar and circular. We use these 7 orbits to perform numerical SPH simulation with the code Phantom in 3D, using gas and 11 grain sizes. The movie you're about to see here shows the evolution of the gas phase. The top row shows the plane of the sky, while the bottom row shows the perpendicular plane. You can notice that our initial orientation of the disk is different in each case because the disk precesses, and we're interested in recovering at the end of the simulation the current observed orientation of the disk. We ran in this case the simulation for 10 orbits in order to reach a steady state for the gas phase. Let's zoom in on the plane of the sky view, and we can see that the different orbits result in different morphologies for the disk. Now, to compare those morphologies to the observations, we need to run radiative transfer simulations from the results of this numerical hydrodynamical simulation. And for this, we use the 3D code MCFOST to compute synthetic observations for ALMA. You can see here the moment zero maps of the CO molecule for each of our 7 orbits to be compared to the observation with ALMA on the top left corner. We will start with orbit 6. Orbit 6 is the one that is more closely coplanar, and hence results in the strongest distruncation. So the disk is indeed much less extended than in the other cases, and actually too compact to be compatible with the observations. So orbit 6 is not a good match. Orbits 4 and 5 result in a secondary disk with an emission that is too bright compared to what we can see in the ALMA observations. Those are not good matches either. Orbits 2 and 3 result in 2 large-scale spirals, but their orientation is not correct compared to the observation. So we discard them as well. And orbit 1 produces 2 large spiral arms with the correct orientation, but the southern arm does not reach far enough towards the secondary to be compatible with the observations. Finally, only orbit 0 here seems to be compatible with the orientation of the spiral arms and the overall extent of the CO emission. So this is our preferred candidate from this observation. We also use the channel maps to compare our results to ALMA observations. Here we see the channel maps observed by Rosati et al. And the 2 large spirals result in deviations from the Keplerian velocity in the disk, which are visible in these channel maps as deviations from the usual butterfly pattern. And these deviations, shown in the dotted circles here, are often called kinks. And in particular, they are visible in the southwest corner here, or in the northeast corner in the delta p equals 0 channel more easily. I will only show you the synthetic observations for 2 orbits here, but you can have a look at all the other cases in the paper. Let's start again with orbit 6 in the bottom right corner. We have in the southwest corner a kink that is so small that it's barely noticeable, while in the northeast corner, the kink seems to have the wrong orientation here. So again, orbit 6 is not a good match. On the other hand, orbit 0 produces kinks that have the correct shape and correct location, and orbit 0 is again a relatively good match. You may notice that the brightness temperature for our simulated observation for orbit 0 is larger than that in the actual observations. This is due to the fact that our simulations did not include the inner disk, which intercepts a fraction of the stellar photons, which then reduces the brightness temperature of the outer disk. So our preferred candidate seems to be the most inclined orbit relative to the disk of the plane of the disk. But can it be the case? Can it happen? We used the work from Bate and collaborators in 2000, who studied the orientation evolution of circumprimary disk caused by an outer secondary. And these authors computed the precession period as a function of the orbital period with this formula here, which includes parameters k and r out from the disk and parameters from the orbit A, E, and the relative inclination IREL. And Q here is the mass ratio between the two stars. If we plug in the numbers from orbit 0, we find a precession or a period of the order of 250 orbital period. This is compatible within a factor of 2 with what we obtained from our SPH simulations, plotting the relative precession angle or twist angle between orbital plane and disk plane as a function of the number of orbits. In addition to driving a precession, the secondary also causes a realignment of the disk plane, and Bate et al. Also computed this alignment time scale, resulting in the formulas shown here. And if we again use the parameters from orbit 0, we find that the alignment time scale is about 400 million years. In the worst case scenario where parametric instabilities develop, this alignment timescales can drop down to 8.6 million years. Still, this is longer than the age of the system, estimated at 6.5 million years. This shows that the evolution of the inclination is quite slow, and the SPH simulation show indeed that it is the case for our 7 orbits here on this plot, showing the relative inclination or relative tilt as a function of the number of orbits. The evolution is very slow. So it seems that a large inclination can be observed even after a few million years as the age of the system today. To conclude, our best orbit is strongly misaligned with the outer disk by 61 degrees and is substantially eccentric. While this may not be the true orbit, we are confident that the true orbit is largely misaligned with respect to the outer disk. On this inclined orbit, the outer companion drives the precession of the outer disk, but drives a very slow realignment, and the high relative inclination that we observe can be sustained over much of the disk lifetime. If you want to know more about the interior of the system, namely the inner disk and the hidden inner companion, I encourage you to watch part 2 of this study by my colleague Rebecca Nealon. Thank you for your attention.